Imagine a world where AI doesn't just predict the next word, but understands entire ideas, concepts, just like humans do. That's exactly what Meta's latest innovation, Large Concept Models (LCMs), aims to achieve. With the release of this groundbreaking research, Meta is redefining the way we think about AI. For years, large language models, LLMs like ChatGPT and GPT-4, have dominated AI conversations. They predict text by breaking everything into tokens, essentially advanced autocomplete systems. But here's the catch. Tokens aren't how humans think. Humans don't process individual words in isolation. We work with ideas, context, and higher-level abstractions. That's where LCMs come in, designed to move beyond tokenization, to operate in sentence representation space, an approach much closer to human cognition. According to Meta's paper, LCMs process information hierarchically. Instead of focusing on word-level predictions, they encode concepts, process them at an abstract level, and decode them back into meaningful language. Think of it as translating thoughts into a universal idea system before expressing them in any language. The significance? LCMs can reason better, avoid repetitive errors, and handle long-form tasks with greater coherence. They reflect how we, as humans, tackle challenges, from creating outlines for essays to summarizing stories into key ideas. Meta describes this as explicit reasoning and planning at multiple levels of abstraction, a feature current LLMs lack. Let's talk about the limitations of large language models, LLMs. These systems, while incredibly powerful, are fundamentally flawed because of one core principle: tokenization. LLMs like GPT-4 process text by breaking it down into tokens, fragments of words or subwords, and then predict the next token. This method, while effective for generating text, misses the bigger picture. Here's an example that highlights the problem. When asked, how many R's are in the word strawberry? Some LLMs fail because they treat the word strawberry as a single token rather than a sequence of letters. To them, it's an abstract block of text, not a dissectable concept. Meta's research points out an even deeper issue. LLMs struggle with explicit reasoning and simple comparative logic. While they can solve complex math problems or write essays, they often fail at tasks like answering whether 9.9 is greater than 9.11. Why? Because tokenized systems lack the ability to reason hierarchically or contextually. The researchers argue that humans don't think in tokens, we think in concepts. When we solve problems or process language, we use a hierarchical approach, starting with broad ideas and breaking them down into details. This is why we can compose essays, answer nuanced questions, and adapt to new contexts seamlessly. By comparison, LLMs operate with a bottom-up method, trying to piece together meaning from fragmented tokens. Meta's large concept models, LCMs, aim to bridge this gap by transitioning from next token prediction to next concept prediction, allowing for higher-level reasoning and planning. Now let's dive into how large concept models, LCMs, work and why they're so different from the traditional large language models we're used to. LCMs operate through a hierarchical architecture designed to mirror human thinking. Instead of predicting the next word or token, as LLMs do, LCMs focus on concepts, complete abstract ideas. Here's how this three-layer system works. Concept encoder. This is the foundation. It takes raw text and transforms it into abstract representations or universal ideas. Imagine translating sentences into a sort of mental shorthand that can be universally understood. Concept processor. The middle layer works on these ideas without worrying about individual words. It processes the relationships, hierarchies, and meanings behind the concepts, essentially thinking about the ideas. Concept decoder. Finally, the processed concepts are translated back into readable words, sentences, or even other languages. Here's a practical analogy. Think about giving a presentation. Instead of memorizing every single word, you create a list of key points or concepts. When you present, the words might vary, but the main ideas remain the same. LCMs follow a similar principle. They work with high-level ideas and adapt their outputs as needed. Meta's paper illustrates this beautifully with a story about Tim. LCMs can compress detailed narratives into abstract summaries. Full story. Tim wasn't athletic, tried out for several teams, didn't make it, and decided to train on his own. Conceptual summary. Because he wasn't athletic, Tim couldn't join teams and chose to train individually. This hierarchical abstraction allows LCMs to reason more efficiently, generate coherent outputs, and even adapt across languages seamlessly. What are large concepts, so? How do large concept models, LCMs, stack up against large language models, LLMs, in real-world applications? Meta's research reveals some fascinating results. First, LCMs excel at generating coherent and meaningful outputs, even for long-form tasks. Unlike LLMs, which often struggle with repetition or drift off topic in lengthy responses, LCMs maintain focus and structure by working with abstract concepts. For example, when summarizing a complex story or generating a controlled length response, LCMs consistently outperformed LLMs like Llama. Let's take a practical task. LLMs. When prompted with a long story, they might overemphasize irrelevant details or repeat phrases. LCMs. They condense the story into clear key points, avoiding unnecessary repetition and maintaining accuracy. Another significant improvement is in instruction following. LCMs are better at adhering to specific guidelines thanks to their ability to process ideas hierarchically. Meta's tests showed that LCMs were more reliable when asked to expand or summarize content within strict parameters, something LLMs often struggle with. But it's not just about structure, it's about reasoning. LCMs are designed to handle higher-level abstractions, enabling them to solve tasks more efficiently. For example, when summarizing a research paper, LCMs can focus on the main ideas without being bogged down by irrelevant details, a skill LLMs lack due to their token-based approach models. Meta's research suggests that LCMs could redefine how we interact with AI, making them more aligned with human logic and reasoning. But what happens when we push these models even further? Let's move on to find out. To understand the true potential of large concept models, LCMs, we need to explore their connection to Meta's V-JEPA architecture, a cutting-edge approach to self-supervised learning. So, what is V-JEPA? It stands for Joint Embedding Predictive Architectures, a system designed to mimic human learning. Unlike traditional AI models that rely heavily on generating specific outputs, V-JEPA focuses on predicting the abstract representation of an observation. Think of it as learning concepts and discarding unnecessary details, just like how a baby learns by observing its surroundings without worrying about every tiny pixel. Here's how V-JEPA ties into LCMs. Conceptual learning. Just like V-JEPA processes videos to learn abstract representations, LCMs process language to grasp underlying ideas and relationships. Efficiency. V-JEPA's ability to discard irrelevant details allows for more efficient learning and reasoning, principles mirrored in LCMs. Hierarchical processing. Both architectures prioritize abstract reasoning over low-level data processing, making them highly adaptable for complex tasks. Meta's paper highlights V-JEPA's effectiveness in learning concepts about the physical world with minimal examples. Similarly, LCMs can process a story or document and focus on the core ideas, rather than getting lost in the details. This connection shows how Meta is building a cohesive ecosystem of AI models, capable of reasoning and abstraction at unprecedented levels. For instance, V-JEPA's video data pre-training allows it to handle real-world scenarios, like object recognition or predicting movement with incredible accuracy. This same philosophy is reflected in LCMS, where the goal is to process language as efficiently as humans think, concept by concept. This connection between V-JEPA and LCMs highlights Meta's broader vision for AI, one that learns, reasons, and adapts like humans. But what challenges do these models face, and what's next for AI? Let's explore that in the next section. While large concept models, LCMs, present an exciting leap forward, they're not without challenges. Meta's research identifies critical areas that need improvement and offers a glimpse into the potential future of AI. One significant challenge is the complexity of transitioning from token-based systems to concept-based ones. Tokenization has been the foundation of natural language processing for decades, and shifting to concept prediction requires retraining AI to think in entirely new ways. This includes developing robust concept encoders and decoders that can handle the nuances of language while avoiding misinterpretations. Another issue lies in scaling LCMS. Meta's hierarchical structure is computationally intensive, particularly when dealing with long-form text or complex tasks. While LCMs are designed to process abstract ideas more efficiently, the hardware and energy demands for training and deploying these models remain a challenge. Then there's the question of integration. Meta's vision of blending V-JEPA principles with LCMs suggests a hybrid future where models combine reasoning across different domains, such as language and video. However, ensuring these models perform consistently across diverse applications will take time and rigorous testing. The implications of LCMS are profound. If successful, they could enable AI to reason and plan with human-like adaptability, potentially revolutionizing fields like education, research, and communication. Imagine AI systems that can summarize an entire book, debate abstract concepts, or create a comprehensive project plan with minimal input. The road ahead for LCMs is ambitious, but the payoff could redefine the limits of AI. The big question now is whether these models will live up to their promise. What's your take? Could LCMS truly be the future of AI? Let's discuss. After exploring Meta's large concept models, LCMs, in depth, it's clear they represent a bold new direction in AI. By shifting from token-based processing to concept prediction, LCMs aim to address the limitations of traditional large language models, LLMs. But do they truly live up to the hype? LCMs excel in several key areas: reasoning and abstraction. By focusing on concepts rather than tokens, LCMs mirror how humans think, enabling them to generate coherent, meaningful outputs and tackle complex reasoning tasks. Improved instruction. Following, Meta's tests show LCMs handle tasks with precision, avoiding the pitfalls of repetition and vague outputs that often plague LLMs. Interdisciplinary potential. With their hierarchical architecture and ties to V-JEPA principles, LCMs hint at a future where AI can seamlessly integrate across domains like language, vision, and planning. However, challenges remain. Scaling this architecture to handle real-world complexity will require innovations in computing power and optimization. Furthermore, transitioning from token-based models to concept-based ones demands rethinking decades of AI development. The real question isn't whether LCMs are better than LLMs. It's whether they can redefine the way we use AI entirely. Meta's vision is ambitious, but as with any groundbreaking technology, its success will depend on real-world applications and adoption. So, what do you think? Are large concept models the future of AI or just another stepping stone? Let us know in the comments below. Don't forget to like, subscribe, and hit that notification bell for more deep dives into the cutting edge of AI. As we move into this new era of AI, one thing is clear. The shift from words to ideas could unlock possibilities we've only dreamed of. The future of AI might not just be intelligent, it could be profoundly conceptual. Stay tuned.